Welcome back, everybody. Today we're going to switch gears and we're going to move into the Bootstrap, and it segues in through sampling with replacement. I'll tell you all about it in the next 2 days. So again, this is not mathematically all that steep, although there's a lot of asymptotic issues that I want to talk about in this method. But I want to give you a conceptual understanding of what it's doing. And this almost mimics exactly what you want to do as a statistician. If you could do anything in the world, you would probably say, I want more data. And I want you to do it over and over and over again. And just keep reproducing data sets for me. And so what statisticians usually do with that is they describe the distribution of interest for various test statistics that you might want to study. So let me give you a better understanding of this, and I'll give you a simulation of this. And I'll tell you how the Bootstrap replicates this in a couple minutes. Let's say I want to estimate some test statistic. So say you wish to estimate, and I'll say you get to see some data. XI's, we'll make these IID. Some data from some distribution. So there's some driving parameter set I'm calling theta. And there's some data that you're seeing that's X. And I'll say that you get n of these things. So this X is just a dummy argument for the space of particular possible realizations. And these are realizations that you actually get to see. So just be real clear about this. Maybe F looks something like this. Theta are unknown parameters to you. You don't get to see them. Typically, you don't even know F, and you have to construct it. But in this class, again, I'm always going to tell you what F is. And in a modeling class, you have to model that and come up with something that looks like your data. We can talk more about that in review sessions, what we actually do in practice. So here's our function. X is that space right here. And then the data are stuff that you see in here. And so to sample, what it means to sample from a distribution is that in some intervals, let's just say my interval is this interval, the density of points, the relative frequency of the number of points in that interval is proportional to the area under that curve. That's what it means to sample. So in some interval, if I just repeat sampling, my relative frequency of seeing some number of data points is proportional to the area under that part of the curve. Of course, this is an asymptotic thing. If I just take one data point, then it's going to be somewhere in here. It's not going to reflect the relative frequency that's proportional to the area under the curve. If I see more and more data, it's going to fill that out. And so as a statistician, I always want people to construct a full distribution for me. Go get more data and do it over and over again, and I can see how those data points are distributed. It's something we can't actually do in practice. But we'll pretend. On a computer, we can always pretend. And so, say we want to estimate some test statistic, T of X, where cap X is just going to be a vector of my samples, my n sample draws. Now, of course, there's all kinds of questions. What do you want to estimate from the distribution, and why do you want to estimate that thing? And so maybe this is an estimator of theta. Maybe it's an estimator of some function of theta. It's certainly going to be an estimator of some function of theta because that depends on theta. There are things called ancillary statistics that have nothing to do with theta. And so typically you're not going to want to construct those. We'll be talking about that stuff in chapter 6. So right now we can just let this be something fictitious to us. And the question is how do I estimate this thing? It's going to be some function of the data. And so what you do is you just estimate it. You just compute it. So last time, Jenny said, what would happen if you did Bootstrap on the sample mean? So let's start with that. Say I didn't know anything about any math, and so nobody ever taught me calculus or anything like that, and I wanted to estimate the mean of this distribution. So I'm going to first say that the tails are coming down fast enough that the mean actually exists. So the mean doesn't always exist for every distribution. So just a quick question to you guys. What distributions do you know of that means don't exist for? What's that? Cauchy. So that's a good one. So we'll be coming back around to Cauchys later on. It's one of my favorite distributions to do stuff with. The tails are so heavy that there can be these extreme outliers. They look kind of normal-ish by the eye, but if you sample from them, you'd see these weird deviations pop up. And I'll have you play around with Cauchys in this class. Okay, so I'm going to assume that maybe, for example, this is equal to x bar. As a first example. So x bar is just sum of the xi's divided by 10. So it's just the arithmetic mean. Okay. Again, I'm assuming I don't know any math. This is a bit of a fiction. All of you are in graduate school studying statistics, and you probably know a lot about this test statistic, that this has a particular distribution. If n is big enough, this is normally distributed. So what I mean by that is that if n is big enough, I went out into this distribution, I collected a data set, and I computed x bar, and I end up just drawing what it looks like. So for one data set, so I'll say data set 1, I compute x bar, and I'm going to call this x bar 1. Okay. If you'd like, I'll put it down here. X bar 1. So this is going to be my mean for data set 1. And I end up just drawing it. Okay, so this is x bar 1. And then I do the thing I can't ever do, and it would be very inefficient to do this in the first place, and we'll discuss why. Some scientist comes in, says, hey, I want to learn about x bar, and I say, well, I'll just compute it for you. There it is. And they say, that's not good enough for me. Because I know that if I went back out into the population and I computed x bar again, I'd get a slightly different value. And so they say, I want to understand the uncertainty in this value. And that's what we're doing as statisticians. So I say to them, okay, well then great. Go back out into the population, collect n more data points for me, and I'll do the same thing. So I go back, they go back out into the population, they get data set 2, meaning they go back out and they collect n random samples from this population. And they compute x, and I go through all the labor of computing x bar for them. And then I plot it. I say, oh, x bar 2. It's right there. It's kind of close. They say, okay, well, that's nice. I could have done that. And I say, well, there's more. Go back out into the population and do this again. And do it over and over and over again. And they go back out, and each data set takes them 4 years to construct. So after 16 years, we have that. And then I tell them to keep going and doing it again and again and again. And they end up collecting all these different data sets over and over again. So I'll say they do this all the way down to data set R, where R is going to be my number of replicates of this. And so they come up with this x bar R, and let's just imagine this is a big number. So after 4 million years, they end up giving me that. I draw a histogram of everything, and the histogram looks something like this. Something like that. Lots more points in here. pretty light tails that come down quick. And so I say that's the uncertainty in X bar for n data points. So for n particular data points, this is the uncertainty of X bar, or at least a close approximation to all of that.
N should be the same for all the data sets?
N has to be the same for all the data sets.
If it's not possible.
What do you mean?
For example, when
I didn't say this is my fictitious land that I get to live in, so this is a mental exercise. All of this would not be possible, and this would be very silly. There are central limit theorems that relate to things that have different data set sizes, and it changes all the theory. And so we're going to keep this relatively simple, and we're going to say n is the same. It changes the variance for everything. And so you would come up with a weighted average of everything, and it would look a little bit different. So I can even give that to you as an exercise. What's the distribution of things with different data sets? And we will do data sizes. So it's not possible. That's fine. I'm in a classroom. I'm holding a piece of chalk. Everything is possible to me right now. Okay. So the biggest problem with all of this right here, I would say, is if you have all of this data, what I really have is a data set of size n times r. And I should be computing x bar for that, which is the more precise measurement. And so, and I can't say to the scientist, please go out and get me now a whole bunch of copies of data sets n times r, because it would say, well shoot, why not just compute a data set of size n times r squared? So it has less certainty. And so it's not only just impossible to go out and do this in practice, but it's a total waste of time because you're not being very efficient with your data. But if I could do anything in the world, I would do this for every analysis. I'd say just come up with more and more data sets, whatever distribution this ends up following. I could estimate some very smooth histogram and tell you all about uncertainties. And so our job as statisticians is to not make the scientists go back out into the population and subsample over and over and over again, because it would be excruciatingly inefficient. It turns out we know the distribution of this. It's normally distributed. So theoretically, this is very close to a normal. So very close. If n were infinity, here's the big fiction that the asymptotic statisticians like to talk about. As n goes to infinity, this becomes normally distributed. They almost mean that. There's something a little bit different. The limit doesn't happen that way because the variance is actually going sigma squared divided by n, and that has 0 variance. So there's a slight modification, and I'll talk about that when we get to the central limit theorem. But you get my point. So this starts to look excruciatingly normal. And so what does normal distribution look like? It looks like this. Square root 2 pi, sigma, that's the variance of the standard deviation of the distribution, e to the minus 1/2 x bar minus mu squared over sigma squared over n. So that's what a normal distribution looks like. And we'll be able to prove this later on. And so each one of these sample realizations is the x bar coming from this. The mean of the distribution is where this thing peaks. It's the true mean. So if I ended up going back to my original distribution, it's the true mean of this distribution. So if I ended up computing x, f of x, dx, where I'm going to integrate over the whole space of x, I'm going to denote this like this, omega x. So that's my whole space. This will be mu. And so the associated variance, sigma squared, will be the variance of this distribution. And so I'm going to assume not only does this have a mean? It also has a variance. And so, if there aren't variances, this result won't hold. And so this is the variance for the original distribution. So the variance of x is equal to sigma squared. So the central limit theorem, oh, and I made a mistake right here. There's a divide by root n as well. So the variance is getting decreased in a ratio sense by n. And so the standard error is getting decreased in a ratio sense by square root of n. So all things that we know. So we can't do this. So there's another trick, and this is the Bootstrap. And it's very similar to doing this, but it's something you can do with one data set on a computer. Let me write it down for you. Oh, also, definitions are due this Friday. So that's the fiducial, the classical, the frequentist, the Bayesian. There's other branches, but those are kind of the main competitors. And fiducial went out of vogue, I would say, as soon as it came. And so it's one of Fisher's mild mistakes. So I think he corrects it later on. We'll talk about the history of all of this as we go through the class. Homework 2. So maybe this is homework 1. This is really homework 0. We're going to read through these real lightly. Take a photocopy for yourself by the end of class. See if you still like your definition. So I'll ask you to do this again. Eventually I'll share my definitions with you. So definitions due on Friday. Homework, the problem sets. I said due February the 6th. There's a slight problem with that. Does anybody know what the problem is? It's a Sunday. So I have a very easy rule in my class. If I ever ask you to turn anything in on a day that we're not in class, you turn it in the next time. So never the earlier time. What I meant to say was February 4th. And so I'll always lean in your favor on this. And so what I really mean is the 7th. If you'd like me to go and correct the web page, I can do that, but you can always apply this rule. Just move it to the next in-class period. And I like homework turned in as a hard copy. Then me and the GTA aren't sitting there for an hour printing out all your stuff. So saves us a lot of time. So you just bring in a hard copy, turn it in. My preference is that you do it in LaTeX, but that's only because I want you to learn it. So what I thought was very important when I was going through graduate school is doing the problem, spending all the time reading about stuff, messing up, eventually getting it right. But if you do typeset it, you'll remember it in the future. It's a good copy for yourself. If you don't want to do that, you don't have to. Just make sure you write it up legibly, very neat. So if you're turning in your scratch work, we're going to be very annoyed while we're grading it. So I'm not going to say I'm not going to accept it, but it's not going to make us feel very good as we're grading everything. And if we can't find your stuff, we're going to mark you down unnecessarily. So at least try to write it out. I know some of you have penmanship problems. I do as well. I was always considered a very sloppy writer. Here's my trick. Does anybody see what it is? I write in all caps. So, and then you can read it. So very easy trick for those of you that have really bad cursive or something like that. In fact, don't use cursive in this class. You can never read your cursive. So again, if you have to do it, that's okay. All right. Hopefully everybody understands the rule. I'm sure it'll happen again. Usually what happens is I'm looking at the wrong year's calendar. So something like that. So I've got like a 3-year ago calendar still on my refrigerator. So something like that. So sorry, it's probably a problem that's not going to go away. So, but with my rule, you get a benefit. Okay, so the Bootstrap is trying to replicate this idea, going back out into the population, but it has a shortcut. But surprisingly, it works pretty well. So I used to say this was my least favorite tool. I used to say the Bootstrap was a cheap excuse for a posterior distribution. And I kind of mean that still, but it's cheap in the sense that it's easy to get. And so now I kind of mean it's cheap in terms of it's inexpensive. It's computationally expensive, something that you couldn't do maybe 200 years ago. They used to have something called a jackknife. And if you've ever heard of the jackknife, just throw it away. So I don't know why people even talk about it. It's like bootstrapping, but not quite. And I'll say something about it, but I don't know why we talk about the jackknife still. It's like for historical record. It's like the bootstrap, but worse in every single way. Okay. So now with modern computers, computing is cheap. And so we can always do this sort of thing. And this is going to apply to an IID distribution. There are other variants of the bootstrap, block bootstrapping, that can help with dependencies. There's mild approximations that are made. You always have to convince yourself those approximations apply in your case. So you can always work this out for a simulation study. Okay, so the bootstrap. Now, I can tell from all the head nodding, a lot of you know what the bootstrap is already. When do you learn it? Undergrad? Now they teach it in undergrad, something like that. I remember being really impressed. I was a math major when I was in college, and I would go like troll the statistics department, I'd troll the physics department, go bother my GTAs and instructors, talk to them about stuff. And I remember hearing the statisticians always saying, well, just bootstrap it. And I was like, oh wow, I've got to learn this thing. This is going to be amazing. And when I got to my first year of graduate school and I learned about this, I was like, that's it? And it bothered me. So it's like, bootstrap. You know, I can get a PhD too. So there is more to this. Brad Efron wrote a book on this. I have that book. You pretty much need to only read like 4 pages of the book. And so unless you want to work out in excruciating details all the asymptotics, but I think a simulation study is even more appropriate for studying this thing. In section 10.1.4, they cover this. They start talking about all the methods like delta method. They talk about some Bayesian methods. They talk about the bootstrap, and they try to discuss the asymptotics of everything. And they fall short on being able to do a direct comparison, so then they move to a simulation study. And so I would say, if you're just doing math and there's no sim study, it's not good enough. I understand that the intellectual level of a proof seems better, but a simulation study is convincing as well. And that's what our book does. Way back in the asymptotic section, we're going to start with this. So that when we get to the mathematics of everything, we already have our comparisons. So I'm going to be asking you to do their simulation study in 10.1.4 in a couple weeks' time. I first need to tell you about all these methods. So this is number 1, the bootstrap. Okay, Brad Efron came up with this a long time ago. I'm sure somebody else came up with it as well. It wouldn't be a far leap from something like a jackknife. But somebody help me out. Why do we call it the bootstrap? Where does the name come from? It's definitely like one of those weird names. It sounds kind of cool though. It does not sound like the sort of name a statistician would come up with for something. It sounds like a statistician would call this sampling resampling or something like that. They would try to name it like what it actually is. And it would be really boring. And CS people usually come up with a better name that has a story attached to it. So I'll say this probably happened because Efron is in Berkeley. So he's hanging out in the Bay Area, and they're all pseudo-computer scientists in the stats departments. So good name. It doesn't tell me what it is, though. Where does it come from? Anybody know?
You want us to guess?
Yeah.
Constantly readjusting the struggle here for it.
Yeah, maybe. So I guess there was this old colloquialism of picking yourself up by your bootstraps. So it means you're hosed. Nobody's coming to save you. You got to save yourself. And so it means there's no statistician that's going to work out the math for you in this sort of problem, but there's something you can do. And you can help yourself with this algorithm. It's not a very good punchline. So you're not going to be able to figure out the math, but you've got this computational tool. I try to think in my everyday life, in my career, How do I simulate it? How do I work out the math? How do I do both things? And can I always work out the math? And in some cases you cannot. And so, but I'll always have a computational tool, and then I'll think about the efficiency of that tool and try to speed that thing up. So for every problem, you always have a lot to say about it. Either coming up with a faster algo or saying something about the mathematics. So if you can do both of those things simultaneously, you can write in depth and get lots of nice journal publications. Okay, everything I'm going to tell you today has already been written about. So here's the bootstrap. So it's an iterative algorithm. It's going to go and iterate cap b times. So I'm going to call this the number of bootstrap replicates. We'll talk about this number a little bit, but ultimately it's big enough. We'll say what big enough means later on. This is probably the most popular question in this lecture. How big should it be? And I'm always going to say the same thing, big enough. So, but we'll say how you diagnose that. For those of you that like to go to seminar, if you ever see a talk on bootstrapping where somebody's used it, In-Young Kim will jump in instantaneously and say, how many replicants? And they'll say, like 1,000. She'll say it's not big enough. And she's right, you know. So a lot of people are always trying to finish their sim studies right before the talk, and they're like, I know. They just take a long time to run. So it's going to be an iterative algorithm. In cap B, it's going to relate to cap R, the number of replicates that you're going out into the population. So this is our fictitious going back out into the population and resampling, but we're not going to do that. We're going to go back to our original data set. So we're going to start with cap X. So we have this, our original data set, X1 to Xn. And so what I'm going to do from that is for every iteration in this loop is I'm going to sample with replacement from that. So I'm going to say X cap B, I'll put it down here, is a sampling with replacement this is going to happen n times. And I'm going to sample from replacement from cap X. So that's never going to change. This cap X right here is that original data set. And so what I mean by this is I'm going to go in there, I'm going to shuffle this up, I'm going to grab a value, boom, pull it out. It might be the 17th value in there. I'm just going to sample uniformly from it. And then I'm going to build that into this vector. I'm going to do it again. I'm going to reach in. I'm going to put that observation back, reshuffle everything, pull out another value. I'm going to shove it into this vector. And I'm going to do that n times until this is loaded up. So there's a command in R or in MATLAB. It's called sample. And there's a lot of toggles. You can say you want to do this with replacement, without replacement. You can put weights on everything. And so the weights are all the same. So this is just uniformly sampling from X, which is like uniformly sampling from F. A sample from a sample is a sample. I haven't changed the distribution of that thing. So the weights on F are determined by its density function. The weights here are determined by their replication, how often they're repeated. So just if you think about this, if this was more discrete looking, and this was 3 times higher than that, then I would grab values in here 3 times more often than I would grab values over here, and those would be represented in this vector. And so the frequencies are going to determine ultimately the density heights. They're related to that. So a sample from a sample is a sample. Okay. Sampling from F could be hard. Sampling from this is very easy. It's just shuffling. So that's what we're going to do. This is a Bootstrap replicate. And then what we're going to do is we're going to compute our test statistic, which is just going to be T of X, B. That's the whole algorithm. There's something called a parametric bootstrap. We can talk about that later if you want. But this is totally not parametric right here. I don't need to know anything about this parameterized family. So the parametric bootstrap, just to throw this out at you, say I knew what this function was, and say I could compute something like the MLE, the maximum likelihood value. If you don't know what that is, you'll know soon. But some estimator of theta. I could compute it under each one of these data replicates. So I could use the parametric model to come up with my estimators. And you just do that over and over again. That's the parametric bootstrap. This is a non-parametric incarnation. The question is how did I come up with this function and why? So parametric bootstrap might help you answer that question. So again, for our example, we're kind of assuming this is X bar. And we'll go back to that and see how X bar actually works. But in general, this could work for any test statistic. So we know the central limit theorem, and we think if this thing is working, the distribution of all of these is going to be roughly normally distributed. So just like if I ran back out into the population and resampled over and over again, and I knew what the central limit theorem says, this should recreate something close to that. Any questions about this? Okay. So, at the end of the day, what you do, your output is basically this distribution. So this is going to be your T's, TB, I guess these will be all your TBs that we'll draw right here. And we can draw a histogram for this. Again, I drew it kind of poorly. And the question is how does this histogram relate to this histogram? They're supposed to look roughly the same. So, very similar idea. So instead of running back out into the population, you just run back out into your sample. And you use the variability in your sample to try to understand the variability in F. Now, if we have a very, very small sample n, and it does not look and resemble the actual density function or distribution that you're studying, the Bootstrap can't help you recover that. And so your sample needs to be representative of the distribution. So let's say I never saw those values. All I saw were these. The Bootstrap is never going to help me to understand this mode. So it'll just never get there because there's no samples over there. Where the Bootstrap kind of messes up a lot is in the tails of the distribution. We usually don't see a lot of draws in the tails, and so we're not going to be able to understand the variability in the tails from Bootstrap. So usually the Bootstrap differs just a little bit in the tails from the actual distribution. Let's simulate this and just see how this all looks. I want to point out there's something that is a little bit off, and this is probably the bigger thing that's off, is that these samples right here that we're getting might be correlated if n is small. So let's just imagine if n was 1, so I just have one data point, and I just sampled with replacement every single time. That value is going to be totally correlated with itself. So we're going to lose some of the IID nature of everything. And so if I only had 2 data points in here, then these test statistics would be highly correlated with themselves. So as n gets bigger, so n is representative of the distribution and relatively large, then the bootstrap will work and it'll get rid of that correlation. So because those values won't be associated with each other. You can think about that. So Efron gives you a pretty weak asymptotic argument that says as n goes to infinity, that correlation breaks. So there's all kinds of asymptotics here. There's the asymptotics for how big should that be, and then of course, how big should n be in the first place. And those are questions that in general, we need to know a lot about f to answer precisely how well it's working. And in practice, you can never do that. So if you do all about f already, you could do all of the math, you probably wouldn't need bootstrapping. And so here's one question that helps us to answer this a little bit, is how many possible bootstrap replications are there? Let's just ask a few more questions before we simulate it. So if I just sampled, if I labeled all of these points, I'm not talking about if x1 has the same value as x17. What I mean is that x1 and x17 are distinct replicates. And so if I just enumerated all the different possible samples with replacement out there, how many are there? N to the n, I've heard that answer before. It's not. So that's probably the most common major combinatorics answer.
N to the power of b.
It doesn't matter what b is going to be here. So it just matters on these values right here. So this is approximating it. I'm just doing it by random. So one thing you can do is enumerate all of them and then compute all of the test statistics under that. This is approximating that. And so instead of coming up with every sample with replacement, unique sampling with replacement, and enumerating them, we're lazy. We throw darts and we just grab at these. And usually we don't make this the total number of possible replicates. It can be much smaller in practice. So it turns out the answer is this. 2n minus 1, choose n. If you want to see next time why this is true, feel free to ask. So, but ultimately, if you know about these stars and bars arguments, I'll just quick outline of this. Is let's say my first value is here, x1. Let's say my second value is here, x2, so on and so forth. I'll do it for just 3 values. So they say this is n right here. What I'm going to do this is I'm going to think about the number of partitions that I can come up with all of this. So let me just give you a visual understanding. If I chose this to be my partition, 1, 2, 3, if I cut my partitions all right there, what I mean by this is I've collected x3 3 times. So everything to the right of that. If I think about that right there, actually all I need is 2 partitions. So mentally go back and just think that right here. All you need is 2 lines to do this. So I would say I've got him 3 times. Partition like this, I might be thinking that I've got this, I've got that, right here. I should have done probably that to express that I got x3 every single time. So it's a question of how many different lines in which positions can I cut these in that separate x1, x2, and x3. And how many different rearrangements of these bars in these numbers can I come up with? And it's going to be 2n minus 1. So to partition 3 things, all I need is 2 separators to do it. So this is the total number of rearrangements of my separators and my values. Rn is 3 in my picture. And how many of those am I going to choose? I'm going to choose n of them. And I'll let you think about that. And so from that, I'm going to choose n things out of it. And that's going to be the total number of rearrangements. So why n? Because I don't care about the redundancy of x1, x2, x3. I could shuffle them around. I could have done the same thing with the separators and shuffled them around. So I'm just taking out the indistinguishable ordering of my separators. And that's what this is. What I want to point out is that this number is huge for even small n. This is big. Let's just look at it. So it's kind of surprising how well Bootstrap can work even with just a few values. We'll try to demonstrate this.
Dr. Lieber, quick question, please.
Jenny.
Professor, since we are sampling without replacement, sampling with replacement, is it possible that our bootstrap size is bigger than n?
It is bigger than n.
So, I mean,
the number of bootstrap replicates is going to be much bigger than n. That number is much bigger than n.
I mean, okay, so is it possible that each XB, right, contains more than n elements?
No. We're going to keep this to be n. So again, we're trying to replicate what we've done over here. So we went out and we got the same data set every single time, the same size, so the asymptotics of that data set are the same for every replicate. Otherwise, we're comparing apples to oranges, at least in the variance sense. So we'd be changing the distribution. And so they all have to have the same data set size because that preserves at least the asymptotics of that distribution. Does that make sense?
Yes.
So we want it to seem like we're going out into the population, we're getting the same thing over and over again, but we're doing it with our original data set. Just another question, this one comes up every other year. Why don't I sample without replacement? Get the same data set every single time. So just by shuffling this data set and preserving its size, we're getting an estimation of how this stuff varies. So I wrote a piece of code, and I'm going to have you code this up yourself. It's not very complicated. There's a few toggles in here. There's n. I said n was 31 just for our first run of this thing. We're going to run it several times. Which one? Think that? I was looking at the video and it's a little blurred out if I leave the lights on. So I'm going to say n is 31. I'm going to say R, cap R is my number of replicates going out into the population. So I'm going to compare these two things to each other, both schemes that I've talked about. And then I'm going to have some number of bootstrap replicates. We can look at what this number is later, but it's big, and you should compute it for a few different numbers. So my distribution is going to be a trimodal distribution. It's going to have some weights on there to control this trimodal mixture model. So this is going to be a mixture of various uniform distributions. What I'm going to do for my sampling for each replicate R is I'm going to sample from one of 3 normal distributions. So ran n is a normal draw, normal 0, 1. Ran n plus 10 is a normal 10, 1. I couldn't change the variance of all of these, I just chose not to. So this is a slightly different normal distribution. This is a normal with variance 1 that's centered at minus 10. And this is a normal that's centered at 3. And so what I'm doing is I'm flipping a coin with these three probabilities right here. You can look at my if conditions, and you can see that I'm getting those right. I'm actually doing the inverse CDF sampler for a multinomial distribution. This is just a multinomial coin flip. So what's the probability that a uniform is less than mixture weight 1? Mixture weight 1 is a half. The probability that a uniform 0, 1 is less than that is a half. So it's the inverse CDF sampler, if you know what that is. So I just do that over and over and over again, and I plot those histograms for you. And then I plot everything, and then I'm going to do everything the same way, but I'm going to do it with the Bootstrap. So I'm just going to be sampling not from the original population, but I'm going to be sampling from my vector of draws. My Bootstrap replicates are going to come from the very last realization that I got from sampling R times. So from that R samples, I'm just going to grab the Rth one and I'm going to Bootstrap over it. All of them should behave similarly. They won't behave exactly the same because it's random. And then I'm going to plot everything for you. And I'm going to see if those distributions look similar. So let's just do it. So again, I have a specific R. That's going to control some of the asymptotics. I have a specific N, and I have a specific B. And cat B doesn't need to be cap R. So here's my example. So this is my wish, is to go out into this population and sample over and over again. So you can see these 31 samples coming from those three different normal distributions, the mixture. They kind of look like this. So I don't get the full distribution, I don't get tail behavior. So from this very last replication, I'm going to bootstrap over that. And you might think, well, it's kind of hard to learn about the mode, the tail behavior, what these troughs look like. But this Bootstrap actually does a commendable job of figuring this out. So these are my Bootstrap replicates compared to my replicates of going out into the population. And they look a little bit different. So they don't look exactly the same. So that's a -2 over here. That's a -4. There's something over here. So I saw this value way out here. So the histograms do look different. So the ranges aren't exactly the same. I didn't sample as far into the tail as this one did. And that's what that is. The question is how do I compare these two distributions and see that maybe they're roughly similar? It's hard to tell. So anytime anybody shows me histograms and asks me what the distribution is, I would say I don't know. I can't tell. I can't eyeball a histogram very well. So what's your favorite tool for comparing two different distributions? At least one-dimensional distributions. What's that?
Name the goal of the distribution.
Say it again?
Name the goal of the distribution.
The empirical KS distribution, that's one way to do it. So that's a goodness of fit test. So I like the QQ plot for comparing directly. You could do that, do the cumulative CDF thing. So I'm just going to compare them directly using a QQ plot. And if you don't know what this is, look it up. And I'll come back next time and explain what this plot tells you. But what I'm plotting is the quantiles from these two different distributions. So I'm taking the 5% quantile from one of them, and the 5% quantile from the other one, and I'm plotting them next to each other. Then I look at the 10% quantile, so on and so forth. This is chopped it up a lot finer than that. So it's probably looking at like 1,000 values in here. So it's looking at a lot of quantiles. I think it's probably looking at 500 of them because R is 500. So it'll compare two different vectors of two different sizes. And I think what it does is it uses the quantile size from the smallest vector that you have in there. If you don't put two vectors in there, it'll compare it automatically to a normal distribution. And so this is comparing those two different distributions. If the distributions are the same, the quantiles should line up in a linear manner. And so the intercept and the slope of this line are just going to be dependent on the shift in the scale of those distributions. But in any case, even if they have different shifts in different scales, it'll check to see if their parametric distribution looks about the same, or their empirical distribution. And so that looks roughly linear, except over here on the tail. And we can kind of see that if we compare the right tail. So I like QQ plots because they don't just tell me whether or not the distribution is the same, although your thing you can maybe do in higher dimensions. They show me where it deviates. And I kind of like that. So I like this visualization. This is one of my 2 favorite plots. So we'll be making a lot of these in this class. So we'll come back next time and we'll play around with some of those toggles. Keep in mind, n was small. And the number of replicates was relatively small as well. So let's come back next time and see how this works. We'll look at what this number is, and we'll talk about how big that needs to be. Thanks, you guys. That's it for now.